So we were talking about numerical and graphical summaries of data, and we had finished up the discussion of numerical summaries of data, mean, median, quartiles, IQR, standard deviation, and variance. And we also had a discussion about outliers. And that's all the numerical summaries of data. Now we're going to talk about graphical summaries of data. So just like with the numerical summaries, we often want to summarize a large set of numbers into a picture to make things easier to see at a glance. So someone can just quickly look and see what's going on with the data. So first, graphical summaries of categorical data. We won't use these in our class, but I just thought you should be aware of two of the main ones. So Mr. Windley has 132 Stout 1200 students this semester, and most of those students are freshmen, but here's the breakdown of grade level. So the grade level that students are in is a categorical variable, and here's the different values of that categorical variable, freshman, sophomore, junior, senior, and each of those values of the categorical variable has a count or a frequency. So we can turn those counts or frequencies into a bar graph. Just simply make a bar for each category or each variable of the categorical variable and make the height of the bar correspond to the frequency within that category. Really important note here on a bar graph of categorical variable, these values on the x-axis are not numbers, they are categories, and therefore there's no reason for the bars to touch in a bar graph. We'll see something different later on in a histogram, but in a bar graph, no reason for those bars to touch. You can also turn this into relative frequency. So now if I take each frequency and divide by the grand total of 132, I get a relative frequency as a proportion, and those relative frequencies should add up to 1. Or I can change that proportion into a percent, and those percentages should add up to 100. And so now my x-axis, my y-axis, instead of having frequency, it has relative frequency, but the bar graph looks exactly the same. The main reason why you would want to do relative frequency instead of frequency is this. Suppose I'm comparing the grade level breakdown in Stat 1200 and Stat 2260. So in Stat 1200, we see a lot of freshmen and very little sophomores, juniors, and seniors. But the problem is that there's so many more students in Stat 1200, there's 132 students, and there's so few students in Stat 2260, only 30, that this bar kind of dwarfs everything. And it doesn't really help me show what I wanted to show, which is that the students are older in Stat 2260. So if instead I turn all of these frequencies into relative frequencies for both Stat 1200 and Stat 2260, now these bars for the juniors and seniors in Stat 2260, now those bars kind of pop out because there's a way higher percentage of seniors in Stat 2260 as compared to Stat 1200. So anyways, that's just a little example of why you would want to do relative frequency instead of just frequency, especially when you're comparing two or more data sets. And if you have relative frequencies, you can also easily turn that into a pie chart. Just make the sectors of the pie proportional to the proportion of that categorical variable that they represent. That's really easy to do with software like Excel. Okay, graphical summaries of numerical data or quantitative data. So here's some data on the Dodgers home runs for the 2019 season. This is the number of home runs hit by each member of the Dodgers last year. So this time my variable is numerical, and there's several different ways to display that graphically. One easy way is with a stem plot. So when I create a stem plot, which works out great, by the way, for 2-digit data, the stems over here are going to represent the tens place. So we have 0 in the tens place for all these single-digit numbers, and then 1 for the teens, 2 for the 20s, 3 for the 30s, 4 for the 40s. And then on this side of the vertical bar, we have what are called leaves, which is the ones place. So for example, this 7 right here, this 7 means that one player on the Dodgers last year had 17 home runs. And this 9 right next to it means that one player on the Dodgers had 19 home runs. And usually it's best to put these leaves in numerical order, which may or may not follow the exact order that you were given the data in. And then one other thing, because the stem and leaf plot doesn't always represent numbers like this that are 2-digit numbers. There's usually a legend or a key somewhere off to the side that lets us know, hey, when you see a 4 on this side of the vertical bar and a 1 on this side of the vertical bar, that represents the number 41. So that we know, just by glancing at this, we know this side is the tens place and this side is the ones place. So please don't look at this and think that we have a number 56 in our data set. We do not. And we do not have a number 356. This 5 and 6 represents two numbers in our data set in the 30s, a 35 and a 36. A couple of variations on a stem and leaf plot. If you end up with a lot of data in one stem or two stems, you can do something referred to as split stems. So instead of having one stem for the zeros, you have two stems for the zeros. One stem for the low zeros, 0 through 4, and one stem for the high zeros, 5 through 9, and so on. And if you make the decision to split stems, then you have to split stems all the way, even though some of those split stems might not have any data in it. For example, we don't have any data in the low 20s, but we still need to have a stem for the low 20s. And you'll probably hear me say this repeatedly, but if there's a gap in our data, then there should be a gap in our graph. So there's nothing wrong with having a stem or two that have no data in it. Now, suppose you have a different kind of 2-digit data, like GPAs, 1.9, 3.2, and so forth. Now, the stems are going to be the ones place, and the leaves will be the tenths place. So that 1.9 GPA, there's the 1 there, and then the 0.9 represented here. And if this was actual GPA data like 1.952 or 1.937, you would have to round it off to 2 decimal places. I'm not sorry, not 2 decimal places, but 2 total places. I guess you could say 2 sig figs in order to be able to graph one of those digits over here and one of those digits over here. And notice this data was not in any particular order, so my leaves here are a little bit out of order. And as I mentioned before, it's usually appropriate to put those leaves in numerical order. Then another variation is to do back-to-back stem and leaf plots, which is a great way of comparing two sets of data. So here I have from last year the home run totals for different players on the Angels. So this part of my stem and leaf plot with the Dodgers leaves is exactly the same as what I had before. So all I've done is I've added a vertical bar here, and now I got leaves going this direction for the Angels. So we were talking about before that this 7 represents a Dodger that had 17 home runs last year. Similarly, this 7 over here represents an Angel that had 17 home runs last year. So on both sides, we're going from the inside out. The the stem 1 and then the leaf 7 to make 17. The stem 1 and then the leaf 7 to make 17. So that's, I think, all you need to know about stem and leaf plots. Then there's a dot plot, which is really kind of simple. So to create a dot plot, all you need is a well spaced out number line, and then you simply put a dot above the number line for every number in your data set. And if you have multiple numbers at the same location, then you just have a pile of dots there. And once again, very common mistake is for students to leave out portions of the number line. If there's a gap in my data, there should be a gap in my graph. So this number line going to go from 0 or from 1 to 47 to cover my data and have every number in between on the number line, even if there's no data at a lot of those places. One of the things that's really beautiful about a dot plot is that you can display a lot of data in a compact area. Here's a dot plot that I created with 1,000 dots, but only down here at the very end at 4 and up at the very top at 23, you can tell that it's actually a dot plot. In between, the dots are so tightly stacked and so tightly bunched together that it looks like just a solid black line. Kind of ignore that red line. That was something about the graph that I was trying to point out. But the point is that a dot plot, since you're not actually graphing the numbers, but a dot to represent each number, dot plot is a great way to display a ton of data quickly. Then we turn our attention to a histogram. So building a histogram is actually kind of a two-step process. First, we need to start off with a class frequency table. And there's not really any rules for creating the classes, except that the classes should all have the same width, in this case 10, but there's nothing magic about the number 10. And the classes should touch, so this class ends where the next class begins. So there's no gaps, because as you'll see, there's going to be no gaps between our bars. And every number on our data set has to have a class that it fits into. So the smallest number 1 fits into this class, the number 47 fits into this class. So once you've decided what the classes are going to be, then you just count the frequency of how much data is within each of those classes. And that's your class frequency table. A lot of times on a graphing calculator, it never shows you the class frequency table. It just shows you the histogram. So now we create some bars, one bar for each class, bars touching, and the bar height matching the frequency within each class. So you see these bar heights of 1, 2, and 1. That matches our last 3 classes. And notice my numbering on the x-axis matches my my class boundaries that I was using up here. I have a class from 40 to 50, and I have 40 and 50 marked out on the x-axis. Sometimes you'll get a bar that has no data in it, so it has a height of 0. That's perfectly fine. You could also create an extra column in your class frequency table for relative frequency and create a relative frequency histogram, or create a column in the table for density, which is relative frequency divided by class width, and create a density histogram. Let me show you that on the homework right quick. So on the very first problem on the homework, they have a set of relative frequency histograms where they have percent on the y-axis instead of proportion, and then they have a set of density histograms. So if you notice the last histogram here and the first histogram here, you can see that they are identical. So as far as appearances, if you do relative frequency versus density, it doesn't make a difference. But notice I mentioned that for density, you do relative frequency divided by the class width. So notice this bar from 4.5 to 5 has a height of about 25%, which is 0.25. But also notice that that class width is a half. And if you do 0.25 divided by a half, you get 0.5. So the height of this bar in the density histogram is 0.5. The main difference between these two graphs mathematically is in this graph here, all of the relative frequencies will add up to 100%. Down here, the actual area under the bars adds up to 1. Okay, so also there's nothing magic about where you start the first class and how many classes you have. So with the same Dodger home run data, I could start the first class at 1. The calculator usually starts the first class at the lowest data set, and then I could count by 12s. And if I start at 1 and count by 12s, then I only end up with 4 classes instead of 5. But the histogram is created in a similar way, and notice the histogram has kind of a similar look to it, which is kind of a segue to our next topic, which is shape. Histograms and dot plots give us a great means for visualizing shape. And often we see a shape to a distribution of data that looks like this, with a big pileup of data near 0 or some other arbitrary fixed low number, a big pileup of data on the left with a thin tail of data pointing to the right. Statisticians refer to that shape of a histogram as skewed right. So this would also appear if we had a really difficult quiz and there was a whole bunch of scores piled up near 0 and very few scores coming out this direction. This also happens a lot with data involving money. For example, if we look at the salaries of players on the LA Dodgers, we get a histogram that looks something like this, with a big pileup of data near 0 and a tail of data going to the right. That happens a lot with any kind of money involving, any kind of data involving money. However, sometimes the opposite happens, where you have a big pileup of data on the right and a tail going to the left. And that would be called skewed to the left, or negatively skewed, because you're going, the tail is pointing in the negative X direction. Positively skewed, or skewed right, but positively skewed because the tail is going to the positive direction of the X axis. And a lot of times we see data like that graph, that dot plot I showed you earlier. A lot of times we see data that's approximately symmetric. Not necessarily perfectly symmetric, but kind of a big pile of data in the middle with the tail going off in this direction and a tail going off in this direction. There's a lot of other types of shapes like bimodal and uniform, et cetera, et cetera. There's a lot of other shapes that we could talk about, but these are the three big ones. And then this brings us to a little bit of an esoteric point about shape and outliers and mean and median. So when a set of data is skewed and or has outliers, the median is the best measure of center. So if you were to look up home prices in LA County, I'll look it up right now. If you were to look up, say, average home price, Los Angeles County, almost always you will see that they will report the median. And the reason is, I was just mentioning that anytime you have data involving money, it's going to be skewed to the right. And when the data is skewed or has outliers, you should use median to describe the center rather than the mean. We'll use the mean a lot more than the median later on in this class, but that's because a lot of times we're going to be dealing with data that's symmetric. But the important thing is that the mean can be heavily influenced by outliers and the median is not. Also, when you use the median to measure center, you should use the IQR to measure the spread. So bottom line is, if the data or the distribution of data is approximately symmetric, then you should use mean for the center and standard deviation for the spread. But if it's skewed or there's outliers, then you should use the median for center and the IQR for spread. And we can go a little bit further than this. When the distribution of data is perfectly symmetric, the mean will equal the median. When it's skewed to the right, the mean will be greater than the median, and when it's skewed to the left, the mean will be less than the median. So let's look at two different data sets where the skewness causes the mean and the median to be different. First of all, we have this. So we were looking at this histogram of Dodgers players' salaries, very badly skewed to the right. And the first bar goes from 0.5 million to 5.8 million. And it's very badly skewed to the right because we have two players out here making over 32 million. And the presence of these outliers will greatly influence the mean, but have no impact on the median. And if we do some statistics on this data, you will see that the average salary is about 5.9 million, but the median salary is 1.6 million. Now, if we look back at the bar graph, the first bar, not the bar graph, if we look back at the histogram, the first bar has 30 players in it who make less than 5.8 million. There's only 45 players represented in this histogram, and over 2/3 of them have a salary less than 5.8 million, but yet the one variable statistics are telling us that the mean is 5.8, more than 5.8 million. So again, the mean is a little bit bad description of center when there's skewness or outliers. The median is a much better description of center. 1.6 million is the median salary, and we know as soon as they tell us median that half of the salaries are above that, half of the salaries are below that. Okay, oh, I was going to say in a little bit different data set, like our Dodgers home run data, which is also skewed to the right, but it's not as badly skewed to the right, we will see that the mean is greater than the median, but it won't be as great a difference. The average, the mean home runs was 14.5, the median home runs was 12. So we still have the mean greater than the median. It's just not as big a difference because this data set is not as badly skewed to the right. So again, we have to know about symmetric, or you could say approximately symmetric, and skewed to the left and skewed to the right, and what that has to do with the mean and the median and when we should use each. Final type of graphical summary of data is called a box plot, or sometimes called a box and whisker plot. So now that we have the 5-number summary, you simply draw a number line again and place one dot for each number in the 5-number summary. Remember, our minimum was 1, quartile 1 was 4, median was 12, quartile 3 was 19, maximum was 47, or And if I did the fourths instead of the quartiles, it would be really close to those numbers. I think this ends up being 18 if I was doing the fourths, and this ends up being 4.5 if I was doing the fourths instead of the quartiles. But the point is, you put one dot for each number in the 5-number summary. You do a rectangle around the quartiles with a bar, a vertical line drawn at the median, and then a whisker from quartile 1 to the minimum, and a whisker from quartile 3 to the maximum, and that's it. No calculations required once you have the 5-number summary. That's how it looks in Desmos. This is how it looks on the graphing calculator. The graphing calculator will actually tell you what each of those 5 numbers in the 5-number summary are. Like right here, it's telling me that the median is 12. And there's a way to modify this box and whisker plot so that it can show us outliers. And when you do that, then the outlier has some kind of special symbol, like sometimes it's an asterisk or sometimes it's a square or a circle. But so in our Dodger home run data, this is telling us that the home run total of 47 is an outlier. And instead of this whisker being drawn all the way to the outlier, the whisker gets drawn to the biggest data set, the biggest number in the data set that's not an outlier, which in our case is 36. I believe the cutoff with this, the cutoff for outliers is around 38-ish. So the only number that we have that's an outlier is 47. And the whisker gets drawn to 36, which is our biggest number that's not an outlier. So oftentimes we do a modified box and whisker plot so that the box and whisker plot can display outliers. So that's all you need to know about the graphical summaries of data. Now you should be able to tackle everything on the homework and be ready for a quiz.